Welcome to this talk about Apache Sling and the project Loom. Some notes about myself first. I am a senior software developer at Adobe R&D in Basel. At Adobe, I currently lead the development of data replication infrastructure for AM in the cloud. I'm also active in the open source world as a member of the Apache Sling project committee, and today I'll present how Apache Sling could benefit from the ongoing project Loom. I will start with a short introduction of Loom and talk a bit about threads. With the current Java platform, each Java thread that we start will actually be run as a kernel thread handled by the operating system. From a resource point of view, those kernel threads are not free. They require considerable amount of RAM for their stack, and scheduling them is not super fast. Those runtime costs limit the number of threads that the JVM can handle concurrently, and this bottleneck limits the request throughput that a simple server model like the one Apache Sling is using, where one thread is allocated to each request, can achieve. So far, one approach to scale servers beyond those limitations has been to embrace the async programming model. So the approach works, but it increases the complexity of the code and also the complexity of the operations. The purpose of the OpenJDK Loom project is to change this paradigm by providing much lightweight threads to the Java platform. It's an ongoing project that is not released yet, but it can already be tested thanks to early access builds of the project. This presentation is based on those early access builds. So those lightweight threads are called virtual threads in Loom, and one of the very nice thing is that those lightweight threads, those virtual threads, they actually implement the standard Java thread API. This means that we can leverage virtual threads with very little changes to existing code. The scheduler for virtual thread is also implemented as a Java executor, so one could potentially plug a specific scheduler targeted to a specific use case. So since virtual threads are way cheaper than kernel threads, we could run many more of them. The OpenJDK developer talked about millions of them. So we would no longer need to limit the number of threads that we consume typically via a bounded thread pool. So for services which request handling consists of a lot of waiting time, typically waiting on I/O or waiting on some events, we could think of using an unbounded pool of virtual threads to serve the requests. By doing this simple change, we could expect higher throughput and lower resource usage, and all that without the complexity of async programming. Let's see how this applies to Apache Sling. Apache Sling is a very good match for Loom, and here's why. First, the core Apache Sling APIs like the resource resolver and their friends are blocking. It would be quite hard to add async APIs along the existing ones because Apache Sling itself relies on blocking APIs from a project like JCR. The JCR API is essentially blocking. So the potential to increase throughput while keeping blocking APIs is very appealing to Sling. And then Apache Sling request processing involves fetching thousands of items from the underlying repository to render a page. And each of those repository access translates to waiting for Sling. So this waiting issue is mitigated by the fact that Jackrabbit Oak, for instance, use a large cache in memory. But still, Loom could exploit this waiting time to increase throughput and potentially reduce resource allocated to the cache. Finally, Apache Sling provides a threading module, the Apache Sling Common Thread module, and this module could actually support virtual thread pools, bounded or not, to allow customer code that waits quite a lot to benefit from Loom. Let's see now what should be changed to benefit from Loom. And it's actually surprisingly little. The customer code and the tech stack itself would remain the same. We'd still use Jetty as a web server and rely on mostly synchronous servlets or scripts. The Sling framework itself would require some minor change though. First, we'd plug an unbounded virtual thread pool in Jetty, and we could achieve that via Apache Felix, because Felix has a module that wraps Jetty. So we could we could plug unbounded pool of virtual thread there, and then we'd allow Sling common threads module to run with bounded or unbounded virtual thread pool instead of kernel thread pool, which is the case now, which is the only option now. So one thing we need to be careful of in Sling and in the application code, it's to not block on I/O inside the synchronized block. This is a limitation of Loom at the moment. We need to avoid this because code that does this operation, this type of operation or this pattern, the virtual thread will actually be, they say, pinned to kernel thread, and it will reduce the throughput at the moment. This limitation may be removed in the future or before GA, but at this point we should avoid this pattern, and it should always be possible to do so. And it seems very simple, and actually it is, and I've done most of it. You can check out a project on GitHub that effectively does run Apache Sling with an unbounded pool of virtual thread plugged into Jetty. And once Project Loom will be released, we could probably integrate similar changes into the main branch of Sling and Felix. So I invite you to check this project out. I have also run some benchmark that I'd like to share. The benchmark were done with Jetty alone, so it's not including Apache Sling at this point. The server that was being tested is actually a test server that I quickly built, and it can be configured to serve requests with a specific wait to compute time ratio. The server can also be configured to run with a standard thread pool or an unbounded thread pool of virtual threads. For my test, my benchmark, I simulated requests that take, for which the wait time to compute time ratio is 99.5%, so they mostly wait. And then I compared two different setups. One standard Jetty or default Jetty deployment with a thread pool configured to be 1000 kernel threads. So 1000 kernel threads is a sensible configuration for this type of workload. And then I have a second server that I test, and that one has an unbounded pool of virtual thread. And then I have done various tests, and I varied the concurrency of the request. So it means that I have increased the number of concurrent requests made to the server. I've done the test for different average latencies, for different request latencies. So 1 millisecond, 10 milliseconds, 100 milliseconds, and 1 second. And for each of those, I have measured the resulting throughput. And here is what I get for average 10 milliseconds request. The throughput for virtual thread is the line in blue, and the one for the kernel thread is in green. So what we can see here is that the throughput with virtual threads is higher than the throughput with kernel threads as we increase concurrency. And somehow when the number of when concurrency is very low, the throughput is similar, which is expected, but as we increase concurrency, the throughput increases for virtual thread, but it stabilizes around 40% higher after around 500 concurrent users. When I tried with requests that have a 1 second latency on average. I get a similar result. The increased throughput for virtual thread is around 60% at best, but the general picture is the same. Those are only preliminary results, but they show pretty appealing increase and the opportunity to save resources. Before the release or after the Loom release, potentially this throughput gain will even increase, but for now it's already quite promising. While running the test, I monitored the resource usage at the OS level using the top command, and here's what we can see for the standard Jetty thread pool, the server that runs with the standard Jetty thread pool. We can see that there are 1,000 threads hanging around, and their individual CPU usage is very low. It's always around 1% or so. The picture is quite different when we look at the resource used by the server configured with virtual threads. We see that for the same workload, with only 11 kernel threads, we can handle the same workload. And the CPU usage for each of those 11 threads is actually much higher than before. So much less threads and much more used. It's also interesting to observe that the scheduler being used by Loom is the Java standard fork and join executor. And that's actually, I mentioned in the beginning that this executor could be plugged. That's the default one that comes with Loom at the moment. Memory-wise, I could only observe that the kernel threads use much more virtual memory, but the resident memory seems to be unexpectedly close in both tests. I would have expected it to be a bit different, but that's what I got. That's all for this presentation. I'm hoping to continue on this effort with more tests, particularly doing some benchmarking with Sling while waiting for the Loom GA. Do you have any question? So basically, it could speed up Sling by 40%. For requests that have this type of wait to compute time ratio, yes, the throughput could increase by 40%. Some Sling requests, obviously, either built in Sling or in the customer code, they don't have this type of ratio, and then the potential gain is going to be different. Have you tried to set up Loom in a Sling instance? Yes, so it was really easy to do so. If you look at the GitHub project that are shared in the reference, you will be able to run Sling with virtual threads. Did you run some benchmark tests with lower weighting ratio? Yes, I did as well, and the results are similar, but the potential gain is not that high. I also have a GitHub project where you can check it out. It's linked in the presentation, and there you can see all the benchmarks that I have completed, and the raw results are there. What's the expected timeline for this being GA? I don't know, and I think even the OpenJDK folks don't really know, because if I understand it properly, the OpenJDK project has moved to not planning well in advance, but rather have some sort of shorter sprints of 6 months. And every 6 months or so, they release whatever has the quality to be released. And it's unclear when Loom will be released that way. There are already early access builds of Loom that are pretty stable. I could run all my tests with that, but it's not. There is no official plan yet. I think you said it's running using the shared fork join pool. Are there any concern with that blocking, which would be a serious issue for processing? So as far as I understood from the OpenJDK folk, the only thing we must not do is to block while doing I/O so blocking in a synchronized block, and that should be fine if we avoid that. So just to make it clear, the virtual threads, they are scheduled using this fork join pool, and you may wait in one of those virtual threads, but it's in a synchronized block that you should not do I/O. That's the only limitation as far as I understood. Okay, I hope I have answered all the questions. Thanks a lot for attending this talk, and I'm hoping to continue with this effort, testing, doing some benchmarks with Sling, and waiting for the Loom GA. Thank you very much.